This is a dramatic reading of Argand Plane Crash, a blog by the Stand-Up Physicist, available at science2.0.com. The complex plane should be known as the Wessel plane, after the Norwegian-Danish land surveyor. His paper of 1799, I don't know if you've read it, was actually ignored because few people were reading the preprint server at that time. Mr. Bookshop in Paris got his name associated with the graphing of complex numbers in the plane. It's actually one of the reasons I try to avoid, naming things for people, because credit is usually pretty complicated and often wrong. So let us look at what the Argand plane gets like 100% right. Take an arbitrary complex number z. It has a unique place to call home in the plane and draw its negative. So it just has to jump the origin. Now let's do conjugate and its opposite. So z star and minus z star. It's the conjugate operator that gives the imaginary axis away. The imaginary axis is, if I've got a 50-50 chance, I usually get it wrong, and I got it wrong this time. It's the horizontal one. Okay, it's because the z and the z star are on the right, and one of those has a plus imaginary number, and the other has a minus imaginary number. And therefore, the imaginary axis must be the vertical axis. And because these are algebraically distinct, they must also be visually distinct. Consider that a rule to live by. Now let's think about rotations in the Argand plane. Multiply a number by 1, and z stays in the same spot. Multiply z by -1, and both the real and imaginary numbers flip sign. And again, it jumps over the origin there, but it's kind of like a pie-sized rotation. Now, if you multiply by that z by the imaginary number I, you basically get a rotation of 90 degrees. And minus I, well, that does a rotation the opposite way. Now, notice that I actually made a deliberate science faux pas. I didn't label the axes. Oops, sorry. It's actually not possible, just with rotations, to say if the imaginary axis is horizontal or vertical. So I can't even get this one wrong. But we know that the real and imaginary numbers are algebraically distinct, but visually there's an issue here. Now someone will complain, whoa, that there's not enough information provided. So just consider my sketch of Michelangelo's David. Well, this did not require 2 years of effort to make a 16-footer weighing 6.4 tons. Art is sometimes lost in reduction. And I would argue that a similar thing happens in mathematical physics. Sure, the equations get fancy, but not the images. One must draw the basics right before working on anything fancy. Everyone says that all axes should be labeled. And in fact, I've always operated that way. Marking people wrong if they somehow didn't define things. But then think about what nature's doing. So are there like any axes, let alone an labeled axis? No. Can you at least tag an electron and keep track of it? No, all electrons are indistinguishable. Does nature actually use complex numbers? Yes. all the time in quantum mechanics. Now, if we really want to represent complex numbers accurately as nature uses them, the visualization cannot require labeled axes or tagged points, which are really the same thing. Now, our visual systems are fantastic at analyzing things that don't move. That is why artists use easels. Visual memory is crap. But a well-placed easel allows artists to quickly compare their work to the model. At least if they're realist painters and not abstract expressionists. Now, when I started to make Quaternion animation software, I found out that I couldn't understand what was going on it. Just anything subtle was sure to be lost in the motion. I including the 3 Argand planes with their labels was important, since the things don't, well, quite move. I mean, I did put in some effort to put in a line that moves as time goes on, so you could kind of link all the moving charts together. So let us start with a collection of events that are kind of an inertial observer moving from the time -2 and a location of -1, -2, -3, moving steadily to the origin at 0, 0, 0, 0. Well, there's nothing exciting here. Move along. So now let us flip the scalar. How the point gets to the origin determines how it backs away from the origin. Doing a time reversal requires you to remember what went on, so you can do the reverse. Only a good memory allows a system to do real number or time reversal. Now let's look at a conjugate in an animation. This is a mirror operation. There are 2 points on the screen. That is how a conjugate looks visually distinct. No one can confuse a reflection over the real time axis, that thing that requires your memory, with one over the imaginary or space axis, that is that mirror thing. You always see a pair of events. You know, ever. The real axis reflection requires memory, while the imaginary uses a mirror so one can see double. So for completeness, here is the complete set. It takes some practice, but it can be fun to identify which one is which in these animation loops. So which one is time reversal? Which one is a conjugate? Which is minus conjugate? All right. But let's all see all this stuff in action. Now, here is a third order Quaternion polynomial animation with Quaternion coefficient. And you go, that's odd. It darts around space-time in ways I would have never guessed. Look at a time reversal versus a reversal in space. And actually, I'll let you figure out which is which. And I'll also let you decide which looks more erotic in the complex plane. Now, not only are real and imaginary numbers distinct algebraically, but with the aid of animations, they are distinct visually. If someone asks, what's the difference between real and imaginary numbers? Well, we actually, with these analytic animations, have a new answer. Real numbers are time is money. Imaginary numbers are space is real estate. Money and real estate work together, but they are definitely 2 different things. Reversing reals requires memories of the way we were. Flipping imaginaries employs a funhouse of mirrors. Real and imaginaries are separate. Reversing time does not change how one looks in the mirror, only the behavior looks a little odd. Watches in a mirror still go forward, even if the hands look a little confused. Presuming you have one of those old-fashioned sorts of watches that don't have the numbers. All right, so, people writing books are going to focus on the static images for obvious technical reasons. Nature, though, is dynamic. And it's about time to update our view of the complex plane from a bookshop in the early 1800s to Science 2.0. Join the evolution. So here's my snarky puzzle. Ever only lasts until a counterexample is found. So a circle in a complex plane has so much space-time symmetry. It goes out as it comes in. There are always 2 points on the screen. So discuss how you would find the origin, the where, and the when of it all. Thank you very much.